Okay. Hello, Mr. Hatchell. How you doing? Welcome to
Hello,
JobPod.
how are you?
Yeah, really good. Thanks. Really good. Looking forward to going through some of these bits on global hazards and seeing how we can support our students in the wise words of Mr. Candlin.
Yes, welcome all. So we are going to start today by looking at the second part of global hazards. So the previous jog pod you will have seen would have been on tropical storms, and this one is now on plate tectonics. And without further ado, we're going to start straight away. And one of the very first things in this topic that you look at is the structure of the Earth. So I'm just going to zoom in for you so you can clearly see what we are looking at. The structure of the Earth then is broken down into three main sections, but one of those sections is broken into two. So we'll start from the very middle of the Earth, and that is the inner core of the Earth. Now, the inner core of the Earth is around 5,000 degrees. It's mostly made up of iron and nickel. It's solid, and it's therefore really, really, really dense, but also very hot. Now, as you transition out of the inner core to the outer core, which is just outside of the inner core, what you find is that that solid nickel and iron melts. So it becomes a liquid layer. And again, it's slightly less hot, so it's less than 5,000 degrees hot. And then as you go further out towards where we live on continents, you will get to the mantle. Now, the mantle is made up of what's called molten rock, and that is essentially magma. That's around 2,900 kilometers thick in total. And the heat and pressure in here means that the rock becomes magma, and it's in a state of convection. So it's, for example, think about a room and think about a radiator in a room. The heat rises, it cools when it gets to the surface, and it falls. And we will look at convection currents in a minute. And then finally, we've got the crust. Now, the crust has variations in thickness, and it goes up to about 70 kilometers deep, but it's about 5 to 10 kilometers deep beneath the ocean. And it's made up of several very large plates and lots of little small plates. And those large plates particularly are the continents of the world. Mr. Unite, any questions?
Yeah, just would it be true that there are two main types of crust? So I know we'll come back to it a little bit later, but are there two main types of crust we might be interested in?
Yes, there are. There are two main types of crust we are definitely interested in. One of them is the one in which all people live on, and that is a continental crust. And the other is where all of our water is stored. That is oceanic crust.
Excellent, thank you, sir. And just out of interest, in terms of the type of rock, so there's granite and basalt. Which one relates to which in that? Because obviously some of the rock is created through plate bounds that we go through later. But where do we get like basaltic rock from in terms of the structure of the Earth, sir?
Where do you think?
Well, we're going to get it from the mantle, sir. So the mantle rises up and it cools and it creates our new rock, and then our continental crust is the granite, which when we get to sort of subduction later on is pretty interesting. But yeah, no, just thought we'd add that little link in there. So
And
what goes on inside the mantle, sir?
What do you think? What's the feature called when the magma comes out of the crust to create that rock?
Feature when it cools?
Yeah. What's the event?
Oh, I feel like I'm. Oh God!
When magma comes out of the crust.
Well, just an eruption.
Yep, it's a volcanic eruption.
Well, I was wondering that. I was like, is it that simple? Am I missing something?
Yeah.
Is it something from university? No, excellent, sir. I was like, yeah, no, it is. It's from erupts, and we've got our constructive and plate boundaries and stuff like that. Excellent. Well, no, really good, sir.
I just thought I'd throw that in there.
No, it's really good. So what sort of key process do we need to know about that occurs in the mantle, sir?
So that is definitely correct convection currents. Okay, so in the mantle we have what's called convection currents, and I mentioned earlier a radiator in a room. If you think about a radiator in a room, heat always rises. So when you turn the radiator on, the heat rises up along the side of the room. When it gets to the roof or the top of that room, it then has to spread out because it can't continue going upward. And as it spreads out, it cools down. And when it cools down, because it becomes cool air is more dense. And therefore, if it's more dense, it falls. So that cool air falls back down towards the ground. And it starts to heat up again as it gets closer to the radiator. And that's a constant cycle. And actually, that is a way in which you can remember convection currents. So essentially what happens is you've got all of this magma, which is molten rock, in the mantle. The magma is, let's say, close to the outer core. So it's hotter closer to the outer core, so it heats up. Because it's heated up, because it's in a hot state, it's going to rise towards the crust, which is continental and oceanic. When it rises towards the crust, it's putting pressure on the crust itself. If there are any weaknesses, that may create a volcano. But generally, it moves along the crust until it cools down to a point at which it becomes more dense and it starts to slowly sink. And then it goes back down towards the core again, the outer core particularly, and it starts to heat up again. And that is a constant cycle or process that continues in the mantle. And that is actually what causes our tectonic plates to move.
Oh, well, that's interesting, sir. Just out of interest, is there a link between convection currents and convectional rainfall that we did in sustaining ecosystems? Is there a
There
link?
is.
Theory behind?
There is definitely. So convection is all about what, Mr. Unite?
Well, the warming up of well, a material or a state. So in the rainforest, it's all about the heating up of the rainfall that had fallen from the previous day, so moisture on the trees, etc. It evaporates into the atmosphere, then cools, condenses, and falls back down, and it lands on the leaves in a process called interception, or ends up within the trees and through transpiration gets released again to the atmosphere. So it's that heating and cooling, like you're talking about with the heater, but just slightly different in terms of almost like trees sweating in a way, and it creates its own rainfall in the rainforest. So no, nice little link there. Thought I saw some similar terms.
And and you're right, and exactly there is. It's a similar process in the sense for tectonic plates. So it's all about that heat element, and it's all about heating up that magma. So that is exactly the link there. It's all about the heat.
Okay, so think about the next little part. Does that mean then I might have plates that might be moving in different directions?
Absolutely, yes. And you will have those plates moving in different directions because the heat is transferring in different ways within the magma. It doesn't all go the same way, and therefore it pushes the plates in different ways. Does that help, sir?
Yeah, it does. Excellent. So I believe there are a couple of plate boundaries or plate margins that we can find out about here, sir. What we got?
There absolutely is, and we've named these plate boundaries or margins differently because of the different ways in which they move. And remember, as I've just said, they only move in different directions because of the way in which the magma is pushing upon the plates to move. And that's because of the convection currents. And so there are 4 types of plate margins or boundaries you need to be aware of. And you can see them on screen now. Destructive, constructive, conservative, and collision. So I'm going to go through each of these now, and we're going to talk briefly about what way they move and what happens as a result. So let's start with a destructive plate margin. Now, a destructive plate margin is when 2 plates move towards each other. And when they move towards each other, the denser plate subducts or goes underneath the other plate. So the plate that's heavier will go underneath the lighter plate. And friction then happens because the 2 plates are pushing against each other, one pushing downward, and land or oceanic crust essentially starts to become magma. That magma is pressurized. And because of the friction, it starts to force itself upward because of how hot it is and the friction that's being created, and therefore can lead to devastating earthquakes and volcanoes due to the friction and due to the heat of the magma. This is the most destructive or dangerous type of plate margin, and that's why it's called a destructive plate margin. Any questions, sir?
No, that was good, sir. I was just thinking about that idea of being destroyed. So you're saying to me that we can have rock that's destroyed, but then how do we not ever run out of crust, sir? Surely if it's being destroyed, we're destroying it and it's creating our volcanoes and stuff, then there must be an opposite reaction, surely.
Absolutely, and that links us straight onto constructive plate margins, sir, because constructive plate margins create new land. That is what they do. So destructive margins destroy land, whereas constructive plates create land. And constructive plates are basically when, as you can see in the image here, the second one down, two plates move apart. When they move apart, they can create what's called a mid-ocean ridge, which is an opening between those two plates. And in that opening, where the pressurized magma underneath is pushing up on those plates, you can see that magma slowly well upward in that gap. And when that magma is moving upward in that gap, it cools. And when it cools, it creates rock. And that rock is, what is that, sir?
And the rock, sorry, sir.
The rock is what? When it comes up and cools?
It becomes igneous rock, sir.
Yes, and it becomes what then? Part of our?
Well, our new land, a new part crust,
exactly.
sir, which is exactly the answer I was looking for when I said about the one being destroyed, sir. We get new rock. So does this mean this is why it's geologically the youngest of our two then, isn't it?
Yes, exactly, it is, because it's always been created, and therefore, and because this is a slow process over time, it takes a long time to happen, and therefore it is our youngest type of rock.
Excellent, sir. So just very quickly, you mentioned about earthquakes. What earthquakes going to be like at a constructive plate margin? Surely they're going to be different to those that occur at a destructive plate margin.
Yes, they're very different. So they are very, very weak. They don't have massive bursts of energy or massive friction like destructive plates do, or like conservative plates do, which we will talk about in a second. So they are really, really weak types of plate margins. And actually, it's a lot like what we experience in the UK with our types of earthquakes, a lot of which most people don't even know happen a lot of the time because they are so weak, because we are on a constructive plate margin.
Excellent. So I really like that. So one of the films I saw the other day on TV, it was a film called San Andreas, sir.
Oh yeah.
And that was with Dwayne Johnson, if you've seen it yourself. But that doesn't have volcanoes there. So there must be another type of plate boundary that doesn't have volcanoes, right?
Yes, there is, and I have seen that film, and it's a brilliant one. Any students watching, please go and watch that film. It's brilliant.
I love the rock. I love the rock.
It's brilliant. So that type of plate margin you are referring to is a conservative plate margin. Now, a conservative plate margin, as you can see in diagram 3, just where the mouse is here, is when two plates slide side by side against each other. Now, they can slide in the same direction or in different directions, like in this image. They do not hit each other head on. They literally just slide in opposite or the same directions against each other. They also slide in different speeds. And sometimes when they are sliding side by side, they get stuck. So they get caught between each other. Now, when that happens, and this is the rock deep under the ground or ocean, when that happens, essentially what then happens is pressure starts to build up. As the plates continue to try and move, they're forcing more and more and more to move. And eventually, when they do move, they let off a big jolt. And when that jolt happens, that is what, sir? What type of event is that?
An earthquake, sir.
It's a big earthquake. And
yeah,
conservative plate margins. Go on, sir.
So go on, sir. No, I was going to say because they have rare earthquakes. So they're less frequent, but they have really powerful ones at these type of plate boundaries. Because as you said about that friction that can really build up. So I see it talks about the San Andreas fault. To my knowledge, they're moving in this sort of similar direction, but one's at a slight angle and a slightly different speed, which is some of the bits you said. So it's definitely one that if the kids want to quickly pause and have a quick little Google, it's quite a cool little margin to look at.
Yes, definitely. The San Andreas fault line is one of the most famous examples of this type of margin. They are both moving in the same direction here, but what happens is one is moving much faster than the other. I think one is moving at, from memory, about 8 centimeters a year, and the other is about
8 and 5. So off the top of my head, I reckon something like that. I reckon.
Yeah, that's exactly it. And therefore, what's happening is the coastline there is being stretched further and further all of the time. And there's actually images online. Go and Google it, of fences that are no longer fences because they've been split and moved apart. It's really cool to look at. So yeah, conservative plate margins, as Sir said, definitely have less frequent not eruptions, apologies. They have less frequent earthquakes. However, they are more severe. And note, they do not have any eruptions. There are no volcanoes created here.
Excellent. So I can see from the last one, I've got a similar sort of movement to my destructive plate margin. But I've got to the same type of crust there? What's going to happen there then?
Yes, so we said destructive earlier was, for example, an oceanic and a continental crust. And because the oceanic crust is more dense, it will subduct under the continental crust. However, with a collision plate margins, very similar to destructive, the only difference is this is two continental plates. So they are both light. Neither of them will sink. And therefore, they are both forced upward. And when they are forced upward, they create fold mountains. And a good example of fold mountains would be the Himalayas. And also, just to mention, these types of plates do also create earthquakes, but they're quite shallow earthquakes. So, in other words, that means that they're not very deep in Earth, and that also means then that they can create a very strong earthquake as well. Mr. Unite, anything to add?
No, that's good. I mean, I'm just thinking we're going to talk about those a little bit later as well. And the only other thing I'd say is the examples are given in terms of Himalayas, San Andreas, and Mid-Atlantic. Is there an example you could give me if I want to talk about a destructive plate margin, sir?
Say again, I missed the last bit of that.
That's right. Is there an example that you could give me for a destructive plate margin?
A destructive plate margin. Let me think. I think the African plate and the Arabian plate are a destructive margin from memory.
Oh, that's a very good one, sir. I was expecting you to go for a nice, easy one off the coast of South America with the Nazca plate.
No, never easy. Always go for the more difficult ones.
Oh, but you got to go in the Pacific Ring of Fire, sir. Oh, that's nice.
Oh yeah, yeah. I love the Pacific.
Yeah,
Ring
that's
of
what
Fire.
I want to segue into the Pacific Ring of Fire. There we go. But what's quite nice about it, sir, is that when we were talking about that destructive and constructive, you were describing to me some different styles of volcanoes. So I can see you've got a shield and a composite cone. What can you tell me about those?
Good. So yeah, there are different types of volcanoes. There are 3 different types, in fact. There are 2 main ones, and then one that's a slight outlier. So let's talk about shield volcanoes first of all. Now, shield volcanoes are, if you have a look over here, are volcanoes that are quite flat. Okay, so it doesn't really have much of a slope to it. It's a gently sloping volcano. So what type of margin do you think creates this? Have a little look.
Oh, well, we're going to be do you want me to answer, sir? So I didn't hear if you said me or the student there.
No, you.
Yeah, excellent. Well, I'm going to reckon we're going to get some constructive plate boundaries here, sir. We know it's going to sort of drizzle out the top. If it's runny, it's going to spread quite far, isn't it? It's going to have what we call, like, that viscosity. And I've sometimes seen those packets in, when you get packages like guitars, and you get silica packets, don't you?
Yeah.
And they absorb water. So I know there's something to do with silica and lava. But yeah, okay, so I can see again, like you say, that it's gentle. But what else is that going to mean, though? If it's a constructive plate boundary, is it going to be violent or not violent?
So it's going to be not violent. It's going to be quite gentle. All right. So shield volcanoes are not explosive. They ooze lava out. And essentially what they create is new land over time as they layer up. And you will also find that these types of eruptions are quite predictable. They happen quite often, and they go unnoticed a lot of the time because you cannot physically see them happening normally because they happen so slowly, if that makes sense.
It does.
Brilliant. So composite volcanoes then are almost complete opposite. So we have a look at this diagram here. It's the second one down. So composite volcanoes are hilly. They have a large slope either side. They're most commonly found on land. They have layers of ash and lava. And very importantly, the reason why they have layers of ash and lava is because of their destructive nature. So these types of volcanoes are destructive. They're found on destructive margins. So they're explosive, they erupt quite quickly, and they cause lots of damage. And therefore, the ash that comes out makes up part of what makes the land sloped. It makes up part of what's in that land. And so essentially these types of volcanoes are very unpredictable. They can happen at any time. And because of the pressure that's always building up underneath the land, because of convection currents, which we mentioned earlier, we find these hard to predict. And that is, I think, everything you need to know about composite volcanoes, unless you have any questions.
No, it's good. Yeah, I'm just thinking about comparisons. So again, some key things, if we to look at some diagrams, you might see about the sort of the wide base versus the tall cone shape, etc. And we've got the alternating layers and not having that a shield volcano. But I also see on the other diagram it's got vents, and there's more vents in a composite cone. Is that to do with it because it's more explosive, so that they would have more vents, or am I missing something there?
No, so it's because they're more explosive, and it's also because of the pressure chamber, the pressure from the magma chamber that's created. So it's like a release almost for the actual pressure that's in the magma chamber. And be aware as well that because there are what are called secondary vents, these smaller vents, because these are also there, they can also, even though they're quite small, create quite a lot of damage on their own.
Excellent, sir. No, really good. Because I've seen the word vent before. We think about vent and anger, so I thought that was a nice one for us to think about. But like I said, sir, I can see we mentioned about Hawaii. I remember being taught at school as well that Hawaii is not on a plate boundary. So talk me through what a hotspot is, please.
Brilliant. So a hotspot is very intriguingly different. Now, a hotspot does not happen on a plate boundary. Now, what we mean by a plate boundary is the point at which two plates meet or separate. So these happen, hotspots only happen inside a plate. So, for example, in the middle of a plate. Okay. Now, the African plate is an example of this. In the middle of the African plate, we have a lot of hotspots. Okay. Now, essentially, a hotspot is where there is a plume of magma, so a chamber underneath the plate of magma that's pushing upwards because of the convection currents, and it essentially eats into the plate. It creates a weakness in the plate, and that means the lava can break through the surface. Now, generally, hotspots are not massively explosive, although they can be. All right, so they can be, but they're generally not massively explosive, and therefore, active volcanoes can occur, and what we get, a real world example of this, is eventually we get an island arc or a chain of islands known as simply islands because the islands have the land has come over the ocean in Hawaii's case. And a good example of this is Hawaii. It's only been created because hotspots exist. And just one more thing to mention, I want to level up your key terms. There is a really useful term you can use for a hotspot in the middle of a plate. A volcanic eruption in the middle of a plate can be referred to as an intraplate volcano. INTRA, intraplate. And that essentially is saying these occur inside a plate. Mr. Unite, any questions?
No, that was really good, sir. I just remember some of my kids being fascinated by the fact that we can know that there's another island that's going to erupt out of the ocean eventually by Hawaii. I can't remember the name of it in about the next sort of 200,000 years. It's already underneath the ocean that eventually appear above the surface shortly. So some really interesting stuff. Just one other quick question. I keep hearing about a volcano called Yellowstone. A few kids keep asking about that. Where would that fit into that, sir?
So Yellowstone is in Yellowstone National Park, and that is in central USA. And that is a very, very interesting type of hotspot. And the reason for that is because it's potentially extremely dangerous. So it's a huge magma plume underneath the Earth, and it has immense pressure. It's created all sorts of geysers, which are areas filled with hot water, and they're being fed by the magma below. And essentially, this is a hotspot that, if it does erupt, will have worldwide consequences, not just consequences for the USA.
That's interesting. So definitely one that a few of the kids have asked about. So now we've looked at volcanoes. Is there anything else we need to know about them, sir, or are we nearly there with them?
We're nearly there. I'm just going to go through one or two more quick things, and then we're going to move on from volcanoes. And I just want us to think about the hazards that volcanoes create. In other words, the problems for people that volcanoes can create. And you've got a list of them here in front of you at the top. So we've got ash clouds, gas, lahars, pyroclastic flows, and volcanic bombs. And I'm not going to go through all these, but what I want to point out to you is that there are a number of different events or problems that volcanoes can create. So it's not just the classic lava That's the issue. It's also the secondary things that creates. Okay, so the ash clouds, for example. Some of you might even remember, some of you listening, although it feels like a long time ago now, the Eyjafjallajökull volcano in Iceland in 2011, I believe. So is that right? 2011 from memory?
Well, I've got 2010 roughly on the sheet just below you. So I think
Oh
2010,
yeah,
potentially, sir.
yeah, completely forgot. 2010.
That is
I was
about that,
actually in
though.
Iceland the year after that, I think it was. And
Yeah.
that volcano is an interesting one because what it did was essentially shut down the whole of Europe for a week, in some parts 2 weeks, because the ash cloud was so severe in the air that airplanes couldn't fly. And therefore, and because it would damage their engines. So ash clouds can also be quite dangerous, although they can be positive too, because the ash that falls from them is good for what, sir? What's the positive benefit of it?
Well, it leads to more fertile soil and increased crop yields, doesn't it, sir?
Exactly, it does.
Yeah, I
So
like it. I
the
like the term yield. I've been trying to get my year 11s to use yield as much as we can.
Yes, exactly. I mean, the ash in the ash cloud itself, that ash is really good for the soil. It creates a very fertile humus layer of soil on the top of any soil, and therefore it actually helps farmers by growing more and more crops. And I'm just going to mention one more thing, pyroclastic flows. Now, pyroclastic flows are basically very, very fast moving. They can travel up to 450 to nearly 500 miles per hour. They're very, very fast moving, superheated gas and ash. And essentially all of the energy from the gas pushes the ash down a hill slope. And you can see it on the image here on the right. And essentially there is nothing stopping these unless the slope dies down. And these can wipe out anything in their path. If you think about a windy day in the UK where wind is 60 miles an hour, these are coming down a mountainside at 450 miles per hour. So these are very, very destructive. And they're just two of the hazards that volcanic hazards can create. Any questions, sir, before we move on?
No, that's really good, sir. The one thing I would get us to think about, make a little cross-curricular link. So with my year 11s, we talk about volcanoes and the impacts on climate. Okay. So is there any ways that they would maybe influence climate as well? You know, because I've seen that's come up when we talked about big events and things like that. You're talking about Yellowstone. Yeah. So yeah, how do volcanoes lead to changing climate?
Absolutely. So it mainly this is down to two things. One, the ash, which creates ash clouds, and two, the actual chemicals that are released by the volcano. So the ash itself, if it's a large enough eruption like Yellowstone would be, it can block out the sun. Essentially, it can plunge parts of the earth into darkness. What that does is it stops the solar radiation from the sun. This is a link to climate change. It stops the solar radiation from the sun getting through that ash cloud, and therefore it actually cools the Earth's climate for a short period of time. Now, when the ash cloud disappears, what actually happens in the long term is that the Earth's climate heats up further than it was. And that's because of the second thing, which is the chemicals released. So, for example, sulfur. When that's released into the atmosphere, or any nitrates, in fact, that has, as we know, an impact on the enhanced greenhouse effect that adds to the blanket that's already there of gases in the atmosphere, and that holds heat inward. It does not let the solar radiation escape from the atmosphere, which in turn heats the environment up. All good, sir?
Yeah, no, really good. Definitely useful for my year 11s.
Brilliant.
I tried to get that concept, so no, good to recap that again now. Thank you.
Brilliant. Now, I'm just going to mention something really quickly here, right? And I mentioned it a few minutes ago. For case studies, you have actually got a jog report available to you of every single case study in the GCSE curriculum. So I don't really want to focus on case studies in this at all because you've already got one of those to look at. However, I will just mention that this says your case study is the Eyjafjallajökull eruption in Iceland 2010, which we mentioned previously. Now, our main focus in this topic is on earthquakes, so you don't necessarily need to do this Eyjafjallajökull eruption, but what it's there for is to give you some context into these types of plates that we looked at earlier, and it's also there to give you some context into the types of volcanoes. So I'm not going to go through that now, but it is there for you to have a look at whenever you feel you need to understand the other things we've already discussed.
That sounds great. Can you just say it once more for us, though, please?
Say what? The name of it?
Yeah, please go on. You say it so beautifully.
Eyjafjallajökull.
Oh, lovely, sir. Let's crack on.
I
Causes of
spent
earthquakes.
6 years in Iceland touring with year 11s in the past, so I had to learn the name somewhere.
Oh, that's really good, sir. Do you know what Yerkel means, though?
I actually don't. Oh, wait. Yes, I do. Sorry. I've just got it. Go on, tell us.
It means glacier,
Yeah.
which is where you get Yerkel Alps from as well.
Yeah, the Yokalabs. Yeah,
That's a story for another
that's
time. Let's
fair.
not go down that route.
When I said I actually don't, and then I went, oh, wait, ice.
Yeah, no,
Yeah,
that's fine. That's
brilliant.
good.
Right,
So earlier we talked about causes of earthquakes. We mentioned about shallow and deep. So I can see we're starting to look at these again, and then there's a really nice sort of introduction there where it's got certain words underlined. How could I maybe use something like that in my revision? What would that be useful for? Those
yeah,
underlined words. So.
exactly. So this is really, really useful. Okay. So what you've got there, where my mouse is now, is a short paragraph. And that paragraph basically explains to you how earthquakes happen, what they're caused by. Now, what's really interesting is these underlined words. If you know these words, if you include these words in any explanation about earthquakes, you will more than likely have hit level 3 or the top level of your answer. Because what these words do is that these are keywords that tell the examiner or your teacher that you understand the processes involved in creating an earthquake. So, plates becoming locked, friction building up, stress created, more and more pressure. That releases, then there's seismic waves. The focus of the earthquake is where it starts. The epicenter is where it moves towards. So, all of those words are really useful in explaining how an earthquake happens. And just to quickly move on underneath that, then, we mentioned these types of focuses earlier, or foci earlier. This is where, remember, the focus is where the earthquake begins. So this is where the stress and pressure was built up, and then it eventually releases. This is where the energy comes from. Now, if we have a shallow focus, what we're saying is that the focus of the earthquake, where it begins, is near the earth that we stand on. Okay, so what that means is the seismic waves, in other words, the shock waves that travel from that focus, are going to have less to travel before they hit us and they impact us. Now, shallow focuses are usually small and quite common. Okay, so they're usually small earthquakes generally. The seismic waves can, though, spread and create quite a lot of damage, and you can get a shallow focus earthquake that is massive. And that is an example of your case study for this topic, which is the Haiti 2010 earthquake. And that is in your case study booklet. And also it is in the jog pod that I mentioned previously. So shallow focuses can be very, very dangerous. On the opposite side of that, we've got deep focuses. Now, these are generally over 70 kilometers, okay, deep in the ground. And these occur on destructive margins mainly. And the damage to these is not very severe. And the reason for that is because the focus is deep. The seismic waves have a lot further to travel to reach land where we have built on. And therefore, the actual damage caused is a smaller amount. And again, just to mention, as I have already done, the focus, as you can see on this diagram, is where the earthquake begins, where the pressure is released. Seismic waves is the energy that travels out of that focus, and the epicenter is where we stand on. It's the 90-degree up structure from where the earthquake has started. Sir, any questions?
No, that's really good, sir. Keep it nice and quick. Anything I'd say we could have had on that, in terms of there's like a fault line, FAULT. So what does that mean? So if there's a fault line, is that linked to the focus in some way?
Good. Yes, it is actually. So the fault line is the point, it's like the plate margin almost. It's the point between the two plates where the focus is. So the focus will be on the fault line, and the fault line essentially separates the two plates in which they are moving. So it is the point at which the two plates almost are meeting but sliding by each other. Does that make sense?
Yeah, that's really nice and clear, sir. So with our seismic waves as well, that would obviously determine the strength of an earthquake, won't it? So obviously, I guess I can measure that somehow. But there must be other ways to measure the damage that's caused by earthquakes. So what can you tell me about the Mercalli and the Richter scale, please, sir?
Absolutely. So I'm going to do this in quick fashion, right? So there are two scales we use to measure earthquakes. Okay. One of them is a scientific measurement, and the other is an observations-based measurement. Now, let's start with the Richter scale on the right-hand side, because this one's the easiest and it's the most well-known. Now, the Richter scale uses a seismograph, which is an instrument to measure earthquakes. It's scientific, which means it's fact-based. It actually measures the energy released in Earth. And it uses a scale from 1 to 10, 1 being the smallest type of earthquake, and 10 being the largest, 10 being very destructive. And the key thing to note with this type of scale is it's what's called logarithmic. And that means that each point in the scale, 1 to 2, 2 to 3, 3 to 4, and so on, as they go up 1 point, they actually increase in 10 times the amount of energy released. In other words, 10 times the greatness of strength of the earthquake. So, any questions on that one?
No, really good, really clear. We're up to about a minute on the Richter scale. Not that I'm timing you on this one. How quickly on the Mercalli scale? So that was a minute on the Richter.
Mercalli scale, 1 minute too. So essentially, the Mercalli scale is not scientific. And what that means is it's not fact-based. What it does do is it bases the earthquake strength on observations, what we see, the impacts. So for example, buildings falling down, buildings shaking, all right, buildings destroyed, and so on. So it starts from essentially very weak. So it starts from instrumental type of earthquake to a cataclysmic type of earthquake. Now, instrumental would be very, very insufficient, wouldn't really know it happens, but cataclysmic would be massive. It would destroy nearly anything in its path nearby. It has limitations in that it is subjective. So we said earlier, it is very, very much opinion-based, and that can lead to problems because different people have different opinions. And finally, one thing that's not on there that I will mention is the Mercalli scale is measured using Roman numerals. Okay, so it's from I to XII, and that is 1 to 12. 1 being the smallest and 12 being the largest. Mr. Unite, happy with that?
Yeah, that was pretty consistent there. So another good solid minute and 2 seconds on the Mercalli. So yeah, Mercalli is really good to compare, damage, I guess. Then so isn't it? We can't. We're not that interested about strength. If we compared Haiti with other incidents, the magnitude and the Richter scale is important. But if I want to think about the amount of damage caused, then the Mercalli is the way to go. So whilst we're thinking about damage, then what things are there that I can do to reduce the damage caused during an earthquake?
Good. So, what we're looking at on screen now is managing volcanic eruptions, but the same and similar things go for managing earthquakes. Sorry, not volcanoes. So we need to look out for warning signs. We need to look for trends. We need to monitor where we can the movement of the plates on Earth. And volcanologists, seismologists do this. And also we need to try and prepare for any potential earthquake incidents. Now, essentially what you've got in front of you now is earthquake management. Okay, so we can do things like satellite surveying, looking at the land to see changes on the land. Laser reflecting, and what that means is it surveys using layers across fault lines. We can use gas sensors to check what gas is being emitted from land. We can use seismometers, obviously, to measure and record them. We can also look at records of previous events and see how often earthquakes occur in a certain area. That might give us a pattern of how often they do occur and when they are next likely to occur. But we can also protect ourselves, not just predict, by, as I said before, looking at the trends. Building earthquake-proof or resistant buildings. So putting buildings on rubber stilts. There's a lot of examples of these in the world, particularly in the USA, particularly on the San Andreas fault line we mentioned earlier, where we build the buildings on stilts, and what that allows the building to do during an earthquake is to vibrate. It doesn't crack it because it's not concreted to the ground. The stilts actually help the building to move with the earthquake. We can raise awareness, as I mentioned before, with being aware of when earthquakes might happen in a certain place. So the public needs to be aware of what to do during an earthquake. And finally, improving earthquake prediction. So improving the technology around how we predict earthquakes and looking at how we can do that as well. So I have a question for you.
Yeah.
And that is this. How can we how do we in the UK basically need to be aware of earthquakes and be ready to act in case there is one? Do you think?
No, sir. It's not applicable to us because, as you said earlier, we're sort of found on the sort of to the east, to the edge of a plate boundary, but we don't get very strong earthquakes that we can feel massively very often. So I wouldn't say we need to be prepared for them. No, sir.
Okay. What about then an earthquake that happened only a month or two ago from now in Leighton Buzzard? That was 3.9 on the Richter scale. That did cause some slight damage to some
What, to
buildings.
Wendy's garden? Are you kidding me? We're talking about hundreds of thousands of people dying in Haiti, not about some woman's deck chair falling over, sir.
Yes, but if that could that increase in scale and intensity in the UK?
Well, I guess so. Potentially, we're constantly moving, as you said earlier, with those convection currents. But I was under the perception we were moving away from that plate boundary, though, sir.
You're right.
That's a nice
Question.
However, to think about the end.
Should we? Here's a moral question. Should we actually build up our knowledge on how to prepare for earthquakes in case we're ever on holiday somewhere or backpacking across Europe for who knows, where an earthquake does happen?
And that's exactly why we should all take GCSE geography, though, sir, isn't it?
Yeah, it is, exactly. Finally, I mentioned earthquake-proof buildings, and I've said actually most of these things, but essentially what we do with earthquake-proof buildings is we build foundations, but these foundations are reinforced. They can be rubber or steel, and they basically allow the building to move while the earthquake is happening. We can also fit windows that are shatterproof, and that avoids injury due to glass shattering, etc. And we can also make the roof stronger with reinforced cement concrete instead of just usual concrete and tiling. And that means that the structure overall is stronger in general. Unless Mr. Unite has anything to add, I think that is all we need to say for this part of the topic, and this is the second part of Global Hazards. I hope you found this useful. Thank you for listening. And Mr. Unite, have you got anything to add?
No, that was really good, sir. I don't want to add anything to it massively, but there was just a term that I've seen that I got talking to my year 12 the other day about, and it's called retrofit, and how we can go back and amend buildings that we've already constructed to make them more earthquake proof. But I was trying to get to think about what the word retro means. Have you ever worn anything that's retro, sir?
Oh, I love a bit. Have I ever worn anything that's retro? Well, what I wore as a child would be considered very retro nowadays. I love a bit of retro, though. I still love a bit of retro. For example, I'm into tape deck still.
Oh, dear.
I love a good tape deck.
Okay, well, on that note, sir, we've remembered that retrofit means to sort of go back and amend existing buildings. But let's go continue this subject elsewhere. But otherwise, well done to those of you that have clicked on today to work through your revision. Obviously, keep working hard, using your knowledge organisers and the other resources we're putting up out there for you, and just keep pushing on with that revision as we go through. But otherwise, thank you, Mr. Hatchell, for leading so well on this. You did a great job. And yeah, perfect. Let's sign off, sir.
Thank you very much.
Cheers. Thank you very much, everyone.